Our next speaker comes to us from the University of New Mexico. Lindsey Rotche is a PhD student, and her work focuses on geographical information systems. The work that she's going to present to us is part of her master's degree. And while she's not studying and working on large data sets, she is a ski patroller at Ski Santa Fe. So please welcome Lindsey.
All right, so I'm going to be talking on something that I worked on, building a new method for recreational backcountry avalanche susceptibility mapping called H-CASM, Human-Centered Avalanche Susceptibility Mapping. So this is really looking at shifting the emphasis of these maps from where an avalanche might start to where humans at risk in the terrain. So starting off with a case study, most of you have probably heard of this one. But in 2019, there was a level 2 ARI course up near Silverton, Colorado. And given the avalanche danger at the time, they were planning to take routes below 30 degrees to stay out of that avalanche terrain. So they pulled up this map, what most of us probably look at, slope shading. And it shows this blue is their route going through, and they did stay in that yellow. And no color to stay below 30 degrees. This was a group of 5 skiers and 1 instructor. So this is a slope they were on. They entered by that gray arrow. Skier 1, the instructor, went first, followed by skier 2. Skiers 3 through 6 stayed up top to maintain eye contact and wait for their turn. And then skiers 3 through 6 ended up triggering an avalanche that caught everyone and also then triggered a second avalanche. So at the end of that, skiers 3 through 6 were up top unburied. Skier 1 was partially buried head above the snow, able to dig out. Skier 2 was buried below the debris of both avalanches, over 2 meters deep. And when they were able to get him out, he did not have a pulse and they weren't able to revive him. So a lot of us heard about this because it really struck the snow safety world of having this level 2 avalanche course and a fatality in it. When CAIC went to the site to measure, they actually measured slope angles from 32 to 34 degrees along that route. This map was made with a 10-meter resolution digital elevation model. They went ahead and made a slope shading layer with 3-meter resolution, and that shows the group was well within avalanche terrain the whole time. So why am I talking about this, and what does this tell us? Well, the first thing is placing the human at the center. So in addition to potential start zones, terrain traps, connected slopes, runouts are all important to the person traveling in the terrain and influence their risk. Number 2, providing the best quality data. While it should be stressed that maps are one tool in a quiver of sources of information, and I really do want to stress that, I'm not saying this is going to change everything. Maps are one tool. It is important that map makers provide the best available data out there. And then 3, incorporating uncertainty. So maps are always going to be a representation of reality. Regardless of your resolution, there's going to be discrepancies and there's going to be uncertainty. So that's where H-CASM comes in, Human-Centered Avalanche Susceptibility Mapping. So that first one, placing humans at the center. So like I said, traditional avalanche slope shading maps, they're going to show where an avalanche might start. But there's other factors that are important to risk. So one of those is the runout. Where's the avalanche going to go? Are you in the path? Terrain traps, so things that are going to amplify that risk. Here I focused on gullies or concavities, where either you're going to get multiple paths funneling into one area, or higher buildup and deeper burials, or cliffs and steep falls, so you're swept off a cliff, you also just fell off a cliff. So, and then connected slopes, so we talk about that 30 to 45 degree range generally. But if you have that prime 35-degree slope slide, that connected, say, 26-degree slope can slide. So it's important to still kind of know where those slopes are and look at them relative to where your main start zone areas are going to be. So number 2, where do avalanches occur? 30 to 45 degrees generally is what we all hear and look at. And the slope did determine the start susceptibility layer and where that's going to be. But there's also all these other influencing factors that play into that, one of which is aspect. This is a really dynamic variable that's going to depend on your storms and your seasons and wind. In this process that I set up, it's in there statically, just based off of the study area I was using, just generals, but those are meant as placeholders so that this could be built in with either the forecast or weather station data to make it more local and dynamic. Distance to ridges, you're more likely to get that start zone within 100 meters of a ridge because of your cornices and tension points. And then the roughness of the terrain. So this is another pretty dynamic one as far as anchoring. So the anchoring is going to happen when your weak layer is below those rough features. Once it gets above, that changes. So this is another one that can be dynamic in there with snow depth and change with that. So what did we add? So in addition to slope determining the potential start zone, aspect, distance to ridges, and roughness influence those and can make it more or less. And this is all done at 1 meter resolution, which is the highest resolution readily available right now. So that last part, incorporating uncertainty. So this is what you're used to seeing when you look at slope shading maps, those categories. And if you look at those categories, they're pretty small. 30 to 31 degrees, 32 to 34 degrees. That's implying that with these maps, we have accuracy to the degree, which we don't. This is false certainty. And so you look at that change and you're like, oh yeah, that's below 30 degrees, but really, we don't really know that. So with this methodology, switching to gradient shading, of keeping it a little more fuzzy, because it is more fuzzy in reality. So same color scheme, but just in a gradient instead of those hard and fast lines. So going back to that case study, the light blue dot is the approximate trigger location, and the darker blue line is the approximate route the skiers took. So if we look at that first start susceptibility layer, you'll see H-CASM versus traditional slope shading. These are made with the same exact digital elevation model, so there's no difference in resolution or the underlying data. But the thing to notice here is the gradient shading versus that false certainty that you're getting. And so that's how the traditional slope shading will stay. But then we add runouts, potential connected slopes, and terrain traps. So the black areas are steep falls or cliffs, so you don't really need to see what's under that. It's a cliff. The darker gray area, that's a concave terrain trap. And while this isn't what we traditionally think of as a gully, it is a bowl where multiple paths are going to be funneled to the same spot. And while we don't know the state of skier number 2 after the first avalanche, what we do know is he was buried by 2 avalanches and much deeper, which just makes your chances of survival lower. So that would show, hey, you're going to get all these paths kind of going to the same spot. Looking at some real paths, these paths are from CAIC. You can see at the top of them, it's that dark reds and purples of high susceptibility for the start zones. Then you can see it's a little faded here, but where it's going to be funneled down in those funnels with the gray terrain traps, and then that peachy color at the bottom is potential runout zones, all covered. So moving forward, this is just the first step. It's not ready to go. Some really important research that we need is how this affects people's risk perception. So are they going to look at these maps and just say, oh, too much, I don't want to deal with that? Or is it going to help people make more informed decisions? Vegetation density, I didn't include that for the start susceptibility or the runouts. I was doing extreme scenarios just to get the maximum runouts and maximum situations, but adding in vegetation density would really help. Making that aspect, and VRM is vector ruggedness measure, but that's the roughness, making those dynamic with the conditions at the time based off weather station data or forecast. So when they say northern aspects are more susceptible today, that would just directly tie in. A more robust, less biased ranking method, so those influencing factors I said, and what's making certain slopes more susceptible, I based it off of a pretty extensive literature review and expert knowledge, but if you use machine learning, you can get a less biased and more accurate result for that, and those could easily just be plugged in again because the framework's there for it. Higher probability scenarios, so with those runouts, I did pretty extreme scenarios to get them the maximum extent, so if you run it again with more likely scenarios, then you can kind of start doing some gradient shading of like, here's where runouts are likely to go, and then here's maximum extent. Validation, we did the best with what we had and the time we had, but doing this in more types of snowpacks with more data and more areas, it was run for near that case study was Red Mountain Pass, so that's the study area for this. Putting it all in a web application like we're used to seeing, like how CalTopo or Gaia or whatever you use is, where you can turn on and off layers. So if you really only wanted to look at that start susceptibility, say, or you were really focused on one thing, you can turn on and off those layers. And then finally, making it open source. So this is all, the methodology for this is freely available. The codes that I made to create it all is free on GitHub. But it uses programs that aren't free. So RAM's Avalanche runout model was used for the runouts, and ArcGIS was used as the GIS program. ChatGPT could make that all open source now pretty easily, but the runout model would be a little harder. But yeah, so that's what I've got. That QR code goes to a story map I created that's a little more detailed about this. I will say it doesn't work as well on phones, but the URL's above it, and you can look at it on your phone. My email, there's a paper in review right now, so hopefully keep an eye out for that if you're interested. And then also a special thanks to Coop for getting me all the data that I used for this. Wouldn't have been able to do it without that. But yeah, that's all.
Thanks, Lindsey. Thanks, Lindsey. That's really interesting work. Do we have any questions? I know avalanche mapping, terrain mapping is a subject near and dear to our hearts right now. Looks like we have a question over here. Brandon's coming down with the mic.
Oh, thanks. I love it, by the way. It's awesome. Is the 1 meter DEM, is that enough to get a view of the actual roughness variability, or would this really go to the next level if you were waiting for 1/3 meter or some other DEM source?
I think actually when you get too detailed, it's almost like there's too much noise. So 1 meter seemed to do pretty well where I like field checked it, but it would definitely be something to look into. Some studies actually will make their resolution a lot less to get the overall things, like some include curvature, which is a big thing when you're looking at avalanches, but in the literature, it's all over the place on what's more susceptible. But like in those, sometimes they'll make it like 50 meter just to get the overall thing.
Okay, great, thank you.
We have time. Oh, Dylan has a question up there.
Have you considered using LiDAR or other mapping techniques just to get that roughness or that vegetation layer and put that into your maps?
Yeah, I actually was looking into using LiDAR to do vegetation density, and it just turned into it's a lot of processing, and you need a lot of processing power for it, and the LiDAR that's readily available out there through USGS isn't classified. So like not only do you have to process it all, you also have to classify it all, and turns into more than you can do for a master's thesis. But I think in the future, LiDAR would be really helpful to get the vegetation stuff. And the digital elevation models are actually coming from LiDAR too.
I think there's a question over here.
So there's the all of the slope angle shading, right, is like LiDAR scans. Were the other layers that you were talking about as far as like terrain traps and roughness, was that all your self-made layers, or was that auto-generated in some fashion? And is there a potential for that to be like an overlay on like CalTopo or something like that in the future?
Yeah, so I made it all, but the process actually isn't too complicated to make them. So roughness is really, you just like plug it into a tool and it'll do it, or into a code. And then with terrain traps, the cliffs were places over 50 degrees. And the concavities, it's this thing called topographic position index, where really it's looking at the elevation of a pixel and then the mean of pixels around it. So if you've got a slope like that and a pixel in the middle, the mean of like some are higher, some are lower, but the mean's gonna be around the same. But if you're in a gully or a ridge, ridges I did the same way but reversed, your pixels down here and everything around you is gonna be higher. So that's how you just take the lowest standard deviation to get the gullies and the highest standard deviation to get the ridges. And that could totally tie into CalTopo or whatever pretty easily. They could process that. It's the same underlying data they're using for slope anyways, an aspect.
There's a booth in the corner. Do we have time for, one question here?
Was the data you used with snow or without snow for the elevation modeling?
It was without snow. Yeah, it was just like the bare earth surface.
Great. Well, thanks, Lindsey. That was really interesting.
Thanks.
Thank you very much. Okay, our next speaker is Nata de Leeuw. Nata started her avalanche career working as a ski patroller at Castle Mountain Resort in Alberta, and she's currently a graduate student at Montana State University. She's going to give us a couple of talks today, and well, I'll just let her come up and start the first one. Nata.
All right. Hello, everyone. Thanks for having me here down in Colorado. Oh, where's the clicker? Oh, there it is. All right. Yeah, got it. All right, so this first talk that I'm going to give this morning is also a master's research project. And I'm going to be talking about meteorological controls on wind slab physical properties. This is the same or similar talk that I gave at ISSW for anyone who missed it, where I was fortunate enough to not get COVID, so lucky me. Okay, so before I get into my actual master's research, I'm going to talk a little bit about what my motivation for undertaking this research was. Like Ethan said, I began my ski patrol, or my avalanche career as a ski patroller at a place called Castle Mountain, which is in southern Alberta. I also grew up there. And you'll hear more about Castle Mountain and southern Alberta's specific weather this afternoon. But one thing about this area is that it's really, really windy. And I just felt like my life was dictated by the wind right from the time I was a child. And so as I began ski patrolling and eventually became a member of the forecast team at Castle, I learned a lot. I learned a lot about how we forecast wind slabs and avalanche problems based on the wind and how we apply appropriate mitigation measures to that. And I think as a forecast team, we did a pretty good job most of the time. But every once in a while, we'd get something wrong. You know, we'd go out and we'd go out heavy with a lot of explosives and it'd just be occasional soft slabs, or the other side of things where it's more dangerous. We'd think we'd have a pretty casual day and we'd get out there and, you know, be on the radio asking someone to go build us more shots. So every once in a while we'd get it wrong, and this was confusing to me as a new forecaster because a lot of the people I worked with were really experienced and had been in this area for a long time. And so I just started to wonder, where are those missing pieces? And can we learn more about this? Okay, so before I get into the specifics, we're going to talk a little bit about some theory of avalanche forecasting, and this comes from Ed LaChapelle. So he said that there are 3 different categories of data we can use when creating an avalanche forecast. And these go from, so we have increasing uncertainty as we move along. So our first category, snow mechanics space with lowest uncertainty, this is seeing actual avalanches, because if you're seeing actual avalanches, you can probably be reasonably confident in the avalanche forecast that you're writing. The next is this snowpack structural space. And this introduces a little bit more uncertainty. Maybe you haven't seen actual avalanches, but you've dug a lot of pits and you've got a pretty good idea of what your snowpack structure looks like. With some uncertainty, you can extrapolate that to avalanches. And the last is weather. And an example of this is after a big storm or something where you don't have a ton of information. It's still dark out in the morning when you're going to work. There's probably been avalanches, but you don't know where they are. You don't know what they look like, and you don't have a ton of snowpack information about your new storm snow. And this is the highest uncertainty category of data we can have, and I think in a lot of cases, that's where avalanche forecasting exists. So what I wanted to do is a project that would help us make this forecasting process easier by using this data to help us better understand and predict this data. Okay, so this is the question I came up with for my master's thesis, and obviously I wanted to do this in a windy area because that's what I'm familiar with. And that question is, how do meteorological variables influence wind slab properties? Because we know that meteorological variables influence our snowpack structure. Most of us work in the snow. We know that. We've seen that. Previous studies have shown that. And we know that the structural properties of snow influence snow mechanics, so that's avalanche likelihood and size. As your slab layer gets harder and stronger, you're less likely to trigger an avalanche, but if you do, you might end up with a bigger avalanche. And so I wanted to look at this connection here, because if we can learn more about this connection, we can write better forecasts in data-sparse regions. All right, so the explanatory variables I looked at wind speed at the unobstructed height, that was on the top of lift towers, low, 1.5 meters off the ground, and then ground wind speed about 0.5 meter off the ground. I looked at the amount of time the wind blew for, above a threshold capable of transporting snow. I looked at the temperature when wind slabs were forming, and I looked at 3 different humidity variables. And the responding variables I looked at were density and hand hardness of the resulting wind slab. So essentially, I'm trying to use all those meteorological factors on the left to explain the snowpack physical properties on the right. And I did field work because I wanted this to be applicable to practitioners. That's where I come from, and that's where I wanted this research to be able to go back to and help. So what I did is I installed some different sensors in depositional areas, and then I went out and I dug pits, either immediately following or during wind slab formation events. And I chose these 2 field sites specifically. They were at the Yellowstone Club ski area in southwestern Montana, because that's where Montana State University is, and you can only drive so far every day to go dig pits. And all right, so for those of you who know the area, that's Lone Peak, Big Sky up at the top, and the Yellowstone Club's just south of that. I know there's a couple Yellowstone Club patrollers here, so I just want to give a huge thanks. You'll hear from Doug this afternoon. Yeah, the patrollers there were awesome for digging a lot of holes and helping me maintain my weather stations on the days I had to go to class. I chose these 2 field sites. So I had 2 field sites. I chose them based on a series of wind loading potential maps that we made, and then also local knowledge, because a lot of the ski patrollers there had been there for a long time and knew where wind loading was most likely to happen. I also looked at terrain parameters because I wanted to choose areas that had a uniform terrain feature that was perpendicular to the predominant wind direction, so that I would hopefully see uniform loading and have a uniform field area to do this study. And then after I collected 2 seasons worth of data, a lot of pits, a lot of standing around in the wind, I spent a lot of time at my computer. And I only looked at time periods where wind speed was greater than 5 meters per second, which is about 18 kilometers per hour. Don't ask me what that is in miles. I'm from Canada. And so I looked at these time periods, and I assigned each wind slab that I looked at a wind period of when that snow was transported by the wind. All right, let's get into some of the results. So first, we'll look at which of the meteorological variables were associated with density. And the only statistic of all those meteorological variables I looked at, the only statistically significant relationship was with low height wind speed. So wind speed that I measured 1.5 meters off the ground in the depositional zone. And this was, you can see here, it's a positive linear relationship. So as our wind speed increases, the density of the resulting wind slab increases. And that's great. That's exactly what we'd expect, right? All of us have spent a lot of time in the snow and we've watched this happen. And it makes sense. As the wind gets stronger, those grains undergo more mechanical fragmentation as they're transported. They pack more densely in the depositional area because they're densely packed. They form more bonds. They become strong, and they become eventually stronger. So that's great. The second thing we can see from this graph is that there's a lot of scatter around that line of best fit. And if you don't care about statistics, you can tune out for the next 5 seconds. But we had an R-square value of 0.15. So what that tells us that at this specific site, during these timeframes, we were able to see that 1.5 meter wind speed predicted about 15% of the variation in wind slab density. And we can't make perfect predictions. There's a ton of other variables associated with wind slab formation. But I think in this case, 15% is actually still encouraging. I also tried a multiple linear regression for those of you that are into those sorts of things, and had some issues of overfit, so wasn't able to improve on this simple linear regression. Okay, next, let's talk about hand hardness. And so hand hardness I had to look at a little bit differently because it's a categorical variable rather than a continuous variable. We use fist, forefinger, one finger, pencil. And so things are sorted into categories, whereas density, we can have any range of values, numerical values. And I divided hardness into hard and soft, where hard was anything one finger or harder. And I did that because it's consistent with how most practitioners interpret those categories, and also it helps, hard versus soft really dictates what sort of mitigation measures, especially as a ski patroller, you're going to apply. So you can see here in hardness that our low height wind speed and the ground height wind speed significantly differentiated between soft wind slabs and hard wind slabs. And so what we're looking at here is, for example, for our 1.5 meter wind speed hard wind slab, this is the maximum average wind speed value. This is the median average wind speed value, and this is the lowest. And what's really important is to look at these kind of grayish blue boxes in the middle, and the further apart the boxes, the more the difference. Okay, also interesting is that temperature in this case was statistically significant and different between soft wind slabs and hard wind slabs. So when you look at this more closely, though, you can see that even though in general harder wind slabs formed at higher wind speeds, there's a lot of overlap in these two graphs. You can see that except for that one really cold day, our temperatures for our temperature range for soft wind slabs fell pretty much completely within the temperature range for hard wind slabs. So, more information really is needed. And then a caveat that I just want to put with this information is I just looked at meteorological variables, and we all know that terrain also plays a huge role in influencing wind slab formation. So we're looking at just part of the story here. Okay, so we've looked at all the things that relate. What about the things that didn't relate to wind slab physical properties? Well, in this case, I did not see a relationship at these sites during these times between unobstructed, so essentially that's our ridgetop wind speed. I did not see a relationship between this unobstructed ridgetop wind speed and any physical properties of the wind slab. And again, like I said, I didn't look at terrain variables, so in different places, this relationship to wind speed may have been different. But what this tells us is that, you know, I think most forecasting operations are, and ski patrols and stuff are measuring that ridgetop wind speed. And what this shows us is that in all situations, that might not actually tell us the important information that we need to know about wind speed and wind slab formation in our start zones. You can also see that wind period time didn't relate. So the amount of time the wind blew for didn't relate to any physical properties in this case. And again, you know, at some point, you reach a time where there's just no more wind, no more snow to be blown around. You need snow available for transport. So something maybe to look further into and look at different, you know, maybe smaller periods of wind time. And then humidity. I think, you know, all the humidity values I looked at were quite high because blowing snow does increase the humidity of the air. So again, it's hard to know which is causing which in that case. All right, so all this information, all these graphs, what does this tell us that's important? Well, unobstructed start zones may not, in all situations, tell us about the wind speed in our important start zones. And this is where local knowledge is really important. So, you know, if you, at your operation, can understand how ridgetop wind speed and direction influences the wind speed and direction at start zones, you can maybe write better forecasts for your area. I think things like keeping detailed records, looking at wind speed and comparing what you saw for avalanches, or, you know, one thing that I think would be kind of cool is to help unlock and, you know, figure out some of these wind speed things is if you could install temporary lower anemometers in some of your important start zones, and then maybe even come up with a regression of how, you know, a relationship of how did our unobstructed ridgetop wind speeds influence the wind speeds down there. And I think things I'd like to do in the future, I'd like to incorporate terrain metrics into this, like Lindsey said in the presentation before me. Turns out you can only do so much in a master's project. 2 years seems like a long time, and it's not. And maybe incorporate wind direction as well. So with that, I would like to thank my funders, and I am happy to take questions. Just stand, okay, I stand on backs over here.
Thanks, Nadia. That was great. Really interesting stuff. All right, we have time for a few questions. I can't see that well, so raise your hand high.
No.
All right, Ron's got a question here in the front.
You said you weren't going to ask me anything, Ron.
Okay, we'll start over here, and then we'll let Ron warm up.
You mentioned wind loading susceptibility mapping. How exactly did you do that, or is there some resources to go find that? Was it just kind of taking the predominant wind direction and looking at other areas, or any details would be great?
Yeah, so I didn't have time to go into detail about that, but what I did, this was actually just for a class project I got into. I wanted to look at the potential for wind loading in start zones, and I don't know if you're familiar with, there's a paper that talks about, a few papers that talk about potential release area and have a model to predict that based on a number of things, you know, start zone curvature, and I guess vegetation, but wind, speed, and direction is one of those. And so I had a friend who's a data scientist and very good with R code. Her and I worked together and we pulled out just the wind loading potential part. And it's based on wind shelter index. So there's a 2002 article by Winstrel, I think, that kind of explains how that works. But yeah, I have that code. If anyone's interested in it, I can share it.
Very interested in
Yeah.
sharing, yeah.
Cool, yeah, we can chat after. I can send that to you.
Ron,
Did you change your mind?
did you change your mind? Looks like I saw a hand come up over here.
I was just curious what kind of sensors you were using and how often that data was being logged.
Yeah, no, that's a great question. So I used the weather stations that the Yellowstone Club had. I think they're Campbell weather stations. Yeah. And then for the stuff in the start zones, I used the company is Rainwise, and they have anemometers, and I used a brand called Hobo for the temperature and relative humidity. Those were all done every 10 minutes, but the Yellowstone Club stuff was every hour. So I just switched everything so that the temporal variability matched. So I was looking at hourly was I guess the most coarse. that I had, so I matched everything to that.
I think we have time for one more question, if anybody's got a burning one. All right,
Great.
well, okay. In at the last minute.
I'm just curious if any of the other variables during wind events affected any other maybe snow pit results you would have gotten, or like fracture mechanics, propagation potential, or if you even went that far when you were digging pits.
Yeah, sorry, the speaker's a little garbled up here, so I didn't quite catch that. Did you catch it better?
Yeah, we're having trouble because we're behind the monitor.
Yeah,
so.
we can't really
Yeah,
see it
sorry.
super well.
My question was if any of the variables in a wind event affect, like if you performed any stability tests, and if any of those variables had correlation to like fracture mechanics, propagation potential, stuff like that.
Yeah, I did. I did ECTs in all my pits, and there wasn't really any correlation there. I actually looked at a lot more variables than what I put up on the screen, but I just wanted to talk about the ones that are most important. But yeah, no, I didn't see any relationship there. But I think there's a lot of other things going on in between meteorological variables to, fracture initiation and propagation. So I did not investigate that one too in depth.
Great. Thank you so much.
Oh,
Is
he can ask me after.
Deron, did you decide to ask a question?
Oh, no.
Oh,
Sorry,
all right. Well,
I just thought of it. So did you actually measure the correlation between new snow height and then the height in the transport zones? And
Yeah,
was
that's another very good question. So that was on my list of things I wanted to do, but I didn't really have a way to reliably measure new snow height because I wasn't up there every day. And the ski patrollers were measuring it, but they get busy, they've got a lot going on. So I just didn't really have the data to look at that. And so I didn't originally, I did look at the height, obviously, of every wind slab, but the height varies so much, even within one area, and then I didn't have reliable data on the snow before transport to plug that into. But that's a next step that I'd be pretty interested in doing.
all right. With that, we will move on. Thank you so much. Great talk. Okay, our next speaker is continuing a tradition here at CSAW with an outlook for our winter. Lucas Boyer comes to us from the National Weather Service in Grand Junction. He grew up in the Midwest, but has been forecasting the weather in Alaska and now for the western slope of Colorado for several years. When he's not looking at the weather closely, he likes to trail run with his Australian shepherds. So please welcome Lucas.
All right, good morning, everybody. Thanks for having us here in Breckenridge today, and appreciate you all attending and supporting this. And it's, I was thinking about this on the way over. We're all here we all are looking at water in its various state and where it winds up and its impacts on human behavior and safety and whatnot. So it's a shared mission that we can all kind of wrap our brains around, and I really appreciate the conversations that we've had thus far this morning and some really good food for thought for all of this that pour our lives into data analysis and trying to solve scientific problems. So today we're going to talk a little bit about the weather, past and present, and maybe what happens here in the future. I'll try to be brief. I know it's before lunch, and I don't want anyone to get hungry on me and start throwing things at me, run me off the stage. So with that being said, let's get going. So a couple things I'd like to look at today. First thing we're going to look at is an atmospheric river event that we had here this past spring in Colorado. And and just kind of looking at some details that developed. And if I know those of you that follow the weather very closely are probably familiar with this term, atmospheric river, and its impacts on snowfall in the state of Colorado and various water impacts and whatnot. So I thought we would take a look at one event that really characterized the past winter that we had last year, which was, by all accounts, record-setting. It was a pretty exceptional snow year. And then after that, we'll talk a little bit about what maybe we're looking at here this season. As many of you probably know already, we have an El Nino year setting up, and we'll kind of take a look at El Nino versus La Nina that we've been under the last few years. So moving along here, there's the past 3 years we've been under a La Nina cycle, and we had basically this triple dip La Nina, and a lot of folks were kind of, trying to read the tea leaves with the snowfall and whatnot and its impacts, La Nina's impacts. So I threw some numbers together from down in southwest Colorado in the San Miguel, Dolores, Animas, San Juan Basin. And that was where we saw some of the biggest impacts from last year's snowfall and water concentrations in western Colorado. So it's kind of a useful place to look at impacts. So the first 2 years of the La Nina, we saw 86 and 92% of median SWE, snow water equivalent, in this basin. And then forwarding to this past season where we did very well, we finished up there with 176% of median SWE as of April 1st. And I chose April 1st because typically our snowpack peaks out the first week of April in Colorado as a median rule of thumb. And then, you look at the previous year there, of course, it's quite a jump. We went from, below 100% of median to, almost 200%. And in many of our snowtail sites out there in that basin, we saw numbers even, north of 200%, particularly Cascade number 2 at 366%. And then we also did very well in Columbine Pass did very well too. I think they were a little lower here right now. Columbine Pass was like 280% on this map, and I think they went a little higher even after April 1st. So it was nonetheless, it was a huge year for snowfall, last year in the San Juans, and which is, something we're going to get into a little more specifically with the event we're going to look at. Columbine Pass also hit their all-time maxima for SWE basically on January 7th, and they basically wrote the maximum record through May 7th. So that will, stand, I'm sure, for years to come. It'll be hard, for anybody expecting as much snow as we had this past year. It's probably going to be disappointing, unfortunately, over the coming year, just because we had so much last year and it's so fresh in our mind. So with that being said, just kind of looking at the sub-basins here across the state of Colorado. The blues there are your highest values above median. The dark blue is greater than 200% above median. And anywhere we have a dot on that map, those are snowtail sites. And those, you'll see some blue dots scattered amongst the greens and tans on there, which, these are favorable peaks that get a lot of snow on them and tend to do very well. However, if you look at the green shading around them, when averaged out, those smaller, basins didn't do as well on a widespread, liquid equivalent. So just focusing on the blues, though, down there in southwest Colorado, we see, we have, basin-wide blue shading, which means that our, heavy snowpack and high SWE was really well distributed across the mountains and of the San Juans and the Uncompahgre. So that just kind of gives you a picture, kind of a graphic representation of snowfall and the bias in the San Juans last year. Just digging a little deeper here, you can kind of see, I zoomed in a little bit here on the right in the San Juans, and you can kind of see where these individual basins were, all approaching 200%. And then, going, as you kind of spread northeastward, we just didn't get, we did very well, Upper Gunnison's, 144%. And any other year, this would have been respectable. But last year, 144% just isn't good enough. We need, 200 or 300%. So it was a bit ridiculous in some ways. So moving ahead here, so we kind of looking at the San Juans there, and we know that we did very well in the San Juans. So when I was looking at a case study to try to figure out, what we could look at here today and what would be kind of something, interesting to stare at, my eyes kind of, tuned in on a couple of big snow events that we had. And if you look over these, SWE graphs like we do in the meteorology world, we pour over these a lot through the season, and you'll see these big surges in liquid water in the snowpack on these peaks. And, inevitably, your eye is drawn to the big jumps, and that's where, we look for the big storms. So this one really jumped out at me when I started kind of, zeroing in on my focus. And I don't know, some of you may remember this one. This one, I did not specifically remember it until I started looking at some of the data. And then I went back and I read one of the discussions, and one of our forecast discussions that I had actually written, and it dawned on me that, this was, the week of spring, and I believe I wrote something in there to the effect of, the calendar says spring, but, the weather forecast says we are still in the, depths of winter here in, western Colorado, because this was a week that sort of came in and never let up. It was pretty much a solid 3 to 4 days of really respectable snow. So let's get into the map here and take a peek at a couple things. So going back to my sub-basin there in the San Juans, I called this March Madness because these are the SWE graphs that, basically for the whole season. And if you look on the vertical axis there, or the horizontal axis for March 1st, and then you go vertically, you go up above there, you'll see that most of these graphs took a really hard jump upward in SWE values in March. And for reference, we're looking at those red lines represent, and the shading on this, the coloring's a little hard to see, but you'll see that on, where the graphs, I think my color coding on the top right is a little different, but nonetheless, the green there on the top right and then the red elsewhere, we saw these big surges in March, and it really was, the whole month of March was a very productive snow cycle. So moving ahead here, we're going to, kind of look at this March 20th event as it materialized. So synoptic setup, just looking here at March 20th, kind of train your eyes on the west coast of the U.S. there off of Southern California. And then also over kind of looking back into Canada, northeast Canada there, Hudson Bay area. We have a pretty good size trough of low pressure kind of set up over the Hudson Bay, and that kind of stretches back towards the eastern Pacific there. And all of this is kind of pushing under a high pressure, ridge of high pressure that's built over the west coast of Canada. But this is at 200 millibars, and so basically at this height we're looking at, jet stream winds here, and we're looking at steering flow and how this is, where's the jet stream going, and what's the jet going to do? And that's really the main focus here is that we have a strong jet stream, 150 plus off the west coast there, kind of training in on Southern California and Arizona. So let's forward here, and we're going to go lower in the atmosphere. So we're going to go down to 500 millibars, and this is kind of where we start looking at vertical scale movement for weather events. And just looking at the vorticity, which is the rate of spin in the atmosphere, where we see again there off the west coast, we've got really good, strong vorticity, and that's coming in there, in Southern California. So we're, at this point, we're all pretty well prepared for something is going to come across the southern U.S. there, and impact, have some impacts on the southern part of the state here. Going down just a little bit lower, looking at the 700 millibar temperatures, we see a core of cold air in the blue sitting off the west coast. And of note here too is that ridge that kind of shoots into to British Columbia, Alberta there, it's a little bit, you've got some warmer air under that ridge parked between two real, pretty cold masses of air. And so, as forecasting snow, we're under pretty, things have warmed up a little bit here. If you in western Colorado, under this regime, we're kind of under the ridge at this point. It's not a strong ridge because the strongest part of the ridge kind of sits further to the north. But we're looking at where's this cold air going to go and how's it going to impact, moisture and i.e. make snow. And that's the big concern here, obviously, and for this forecast. Looking ahead, and then looking at the integrated water vapor. So this is the tool that meteorologists kind of look at right now, especially for atmospheric rivers, which a lot of us are kind of focused on. And so this is a tool that we use to just see where is the water in the vertical column, and where is it going to go? Where is the atmosphere pushing it? Because it's just, we call them atmospheric rivers because they're essentially, rivers of, the atmosphere is a fluid and it moves just like any fluid. It's just less dense than water, liquid water. But these atmospheric rivers are of importance to us because they're really effective at pushing vast quantities of moisture into the arid west. So that's something we want to look at here. So moving forward, we kind of fast forward, and we've got our event here, and we've set up our jet stream over southwest Colorado. It's blasting us with we've got good frontogenesis here, and we're precipitating nice and properly here on the 22nd. Same thing here with the 500 millibar setup. Vertical motion here with the vorticity max is trained right over the four corners. This is a great place to be if you're looking for weather production right there in the four corners. And then looking at our 700 millibar temperatures, we see that our cold air has diminished some, but we've cooled off, and we see cold air dipping all the way into like Baja, so that we know that we're getting colder. And then just a quick look. So favored regimes for snow here on the west slope, or in Colorado in general. We see that we've got, over there on the left, we've got this northwesterly flow with a high pressure off the west coast. That generally gets, our northern aspects, northern mountains do pretty well under this regime. Then we've got kind of a general open wave pattern here in the middle, and that'll get almost all of our mountains in Colorado. And then last but not least, we have this low digging through the four corners, and that's really good for southerly aspects, and that's why this storm was so good for snow production in the San Juans. And then here's our 72-hour accumulation for that event, and you see pretty good concentrations of 24, 30 inches and above there in the San Juans. So this was a really good producer. And then just looking at some individual snowfall totals and the SWE values we saw, I picked the 19th through the 24th. We didn't really have anything on the 19th. Things started going on the 20th and kind of tapered off on the 23rd. But we've got up there at Mullis Lake, there on 550 south of Silverton, 4 inches of SWE. 3 inches of SWE elsewhere here, and then down here at Wolf Creek Summit, 6 inches of SWE. This was a huge event for Wolf Creek. And this is where we saw some of our biggest jumps in percentage of median liquid water. And we jumped, like this cascade number 2 went from 160% of median to almost 400% of median SWE. So this storm was really super productive. And then looking at the Wolf Creek Summit SNOTEL, I've got a pink arrow there pointing to this storm just, shot the liquid through the roof. We had, I got my pink arrow covered up over here on the right, but 24-hour snow total at Wolf Creek was 53 inches. And then for the month of March, they had 145 inches down there. So these were big events. And then just kind of wrapping up here, looking forward at this year for El Nino and what we can kind of expect. We see under an El Nino year there on the left, we see a wetter storm pattern coming across the southern U.S. Where after last year, it's gonna be hard to imagine a wetter year. But the storm track is pretty good. It's going to be very similar. If we do get some storms, they're going to be very similar, likely to what we saw with the storm we just looked at. As far as La Nina and El Nino years, I just did a compilation for basically the past 20 years or so here, looking at El Nino and La Nina winters, and there's not really a good correlation. We see a lot of variability in both. The red arrows are El Nino years, and the blue arrows are La Nina years. And so there's a lot of up and down variability, and then the color bars represent each month of the winter season, or snowfall season, I should say. And then just looking at past El Nino events, there's not, in the last 20 years, the most recently this fall, we're starting an El Nino cycle. Sea surface temperature anomalies are comparable to 2015, but not quite there. And you can kind of see, I did the SWE graphs for all of these years that I circled that were El Nino years in the past 20 years. And there's a few big years, but there's a lot of years that just hover right around the median SWE value. And then looking back at the 90s, there were a few El Nino years in the 90s that were fairly productive. 1995 was really super productive, but these other 2 years, 92 and 98, were a little bit lower and not quite as productive. And then looking ahead here looking at precipitation anomalies for the season. We see early part of the season here, December, January, and February, we have anomalous, precipitation on the West Coast, a little bit in Utah, and then in southeast of the United States. And Colorado's we're kind of sitting right in the center of these two areas. We forward to the next 3 months, for January, February, and March, we see that Utah signature kind of disappear, but we still hold on to this West Coast signature. And then forwarding into the spring, it looks like the moisture signature moves further east. We lose that west coast signature. And then just kind of looking at temperatures here, we start off warm across the northern tier, equal chances of being above or below average here in the west, in the Four Corners. So, but there's quite a bit of warm air around us is kind of what they're trending towards here. Same with precipitation, warm and dry in the northwest, and then wet across the south. February, March, and April, we see some cold air intrude in the center of the country, below average temperatures. So hopefully we can tap into some of that cold air with some of the moisture and see, turn some of this, green into snow for our late spring season. And these challenges, or the challenges with these long-term forecasts, we kind of have to make broad brush attempts to look at where the forecast is going to lie. But there's some indications that we'll see some moisture come across the southern tier of the U.S., and that could be, like I said before, promising for southwest Colorado. Looks like I'm out of time, and with that, I will kind of hand it over to the audience for questions, and appreciate everybody's attention.
Thank you so much.
Yeah, thank you.
All right, we have time for a couple of questions, and then we're going to try to give you a little bit extra time for lunch. Looks like over here. Wait for the microphone, please.
I'm just curious about the accuracy. Like you hear CSU put out hurricane forecasts. You guys put out El Nino, La Nina forecasts, and I'm just curious, as the public, or we're always forward-looking, or maybe we relate to the 170%, or we remember that year. When you look back in, decades and decades of data, you had we had three La Nina years. One was record, and the other two were below median. What is, it's hard to predict, but what's the accuracy of the predictions over the years?
Well, I can't answer specifically, like we as far as the numerical accuracy of those predictions, and I would venture to say that they're probably not as high, obviously, as we would like. And these are, keep in mind that we're looking at long-term climate trends, over a 6-month period, and we're trying to look, more so. This is a coarse look at. Large time scale, coarse look at the data. And, obviously, weather is a series of small events and peaks and lulls. And so, with these long-term forecasts, you're kind of looking at the big coarse picture, and you're always going to miss those small granular details. Much like the shading of the slopes, where, the path, they miss the path because of the coarseness of their slope shading, led them to believe that they were not in a terrain favored for avalanche. So, we're going to, when these big storms come through, we have to be careful not to let them, say, well, we were right or wrong about this forecast. And so that's why, we tend to look on these 6-month forecasts. We try to look at it as just a very general trend as opposed to a specific trend. And we know that accuracy is going to be hard to pin down when you're just looking at a big blanket, broad swath of time like that. Hopefully that helps a little bit.
Thank God for atmospheric rivers. They're pretty amazing. The SNOTEL slide you showed with all the really high percentages, I noticed that a lot of the lower elevation ones had the highest percentages. And I saw that up in the Yampa Basin where I'm from as well, and anecdotally heard from ranchers and people in Western Route County and Moffett County that we had a lot of low elevation snow. Has anyone been looking at any weather phenomenon that happened last year that created that lower elevation snow?
I don't know. I know there are some folks. We're actually working with some folks on an atmospheric river project that are actually up in the Yampa Basin. I think they're going to be looking at some stuff there specifically. As far as speaking to what, just anecdotally, what, last year's weather, I think a lot of that, like lower elevation stuff, we could largely attribute to just the atmospheric column was much wetter last year. We did not have as much dry air to overcome, and that's our nemesis here in Western Colorado, is overcoming the arid dry and getting liquid to the surface, and it's really challenging, as living if you're a little bit lower elevation, getting rain or snow down to the surface when you start out under a dry air mass. It chews up a lot of your early moisture that comes in. So with these really wet systems, with these atmospheric rivers, as you mentioned, thank you for them. They start out pretty wet, and the column stays wet, and really it makes them very efficient producers of snowfall. And I think that's going to be, if we look at this in retrospect, we'll see that in the data.
I just want to say, back in the day when I was patrolling, we used to call a thing a split jet when it was the El Nino. And that looks from your maps that what we're going to get is another split jet.
Yeah, there's always different branches of the jet stream, to look at, and obviously, we train in on what's going to be impacting us specifically, but that's a term that comes to mind. With El Nino, the big thing that we try to, focus on there and point out is that we're trying to follow, the jet stream is just, it's a differential in the atmosphere of, temperature and the other variables beyond that are impacted there. And so with the jet, with an El Nino, it's a sea surface temperature. It's a big temperature gradient, ocean surface temperature gradient there. So the jet is always going to set up at the strongest, gradient or change. And so it's naturally we're going to be watching that and where it goes. And it's always, keep your eyes on the jet stream. That's the money there.
So I think we had one question up here in the front, and then we'll break for lunch.
Thanks, Lucas. This is piggybacking on that last question. With that lower southerly Pacific jet, how does that influence flow? And could we see more southwest flow storms for the San Juans?
Good question. Personally, I think it gives you a much better chance of southwest flow in the San Juans, and that's why you'll notice my presentation really leaned heavily there, because with El Nino, we typically see that southerly, jet activity. We saw in the precip forecast for the season, we see a lot of, above average rain across the southern U.S. I'm bullish that that will be good for the San Juans. Not to say that Northwest Colorado and Steamboat won't get their champagne powder. It's going to happen, but I think it's going to be harder when you have warm air over the Northwest, and it's just going to be a more difficult path to put that Northwest flow in. Across those mountains. Thankfully, they stick way up there in the sky, and they're really productive, for snowfall anytime you get those orographics. And that's one thing I like to remind everybody with snowfall in Colorado. We always, terrain is on our side and we have lots of good orographics. So if we can just get a little bit of moisture, the orographics, we can usually put some snow on the ground and keep ourselves happy here. But probably not as much as last year, unfortunately, as much as I'd like to see a repeat of that.
So your forecast is for not record-breaking snowfall.
Yep, I'm going to stand on that one
All right.
today.
That's great. Well, thank you so much, Lucas. We really appreciate it.
Yeah, thank you.
Okay, we're going to break for lunch. We're going to start right back up at 1 o'clock, so please get out, get some fresh air. Be back here a little bit before 1, and we'll start with the next talk.